So we have this topic, is very core engineering topic, I would say. You must be hearing a lot of vector search, vector database, right, for quite some time. And especially it got popularized after OpenAI ChatGPT, right, in 2022, late 2022, I would say. But it is not definitely a concept that was derived in 2022. Vector database was there. It is one of the column, I would say, in the information retrieval space. If I'm not wrong, some vector database solutions are there way back in 2016-17 as well. So it's not a new concept, definitely, but it got popularized after ChatGPT came into the market. Here, I'm not going to talk about the use case of vector database, but I'm going to talk about how vector database can be accelerated through the hardware. So a typical term, probably some of you may heard it earlier, called mechanical sympathy, which denotes actually how hardware and software works together, right? So it's not only the software, it's not only the hardware which drives your performance and efficiency. You have to combine them both to get the best out of it, right? And this presentation is trying to address one of that particular feature which are available at the hardware and how we can bring it to the software and improve the user experience. Brief introduction about us. I am Sourav. I'm an engineering manager at Intel Corp. And I have my colleague Abhijit. He's a senior software engineer at the same organization. Not many people know that Intel, many people know Intel is one of the semiconductor giant, definitely, and a technology innovator company, but few of you might know that we are equally into the open source software. If you look at this open source contributor index, you will find Intel as one of the top 10 contributor, sitting along with organizations like Meta, Google, Microsoft. Okay, so open source, we believe in it. We contribute heavily, starting with OpenSearch. This is one of the topics that we have today. The theme of our conference. We are at Intel contributing to the heavy open source project like Linux kernel, PyTorch, and we are making every user life better through our contribution. Okay. So here's a quick look at the agenda. I'm trying to go through this bit complex topic in a much easier way. That's my try. I hope that by end of this session, you'll get some idea that what this alien words, AVX, is all about, and how we can use this AVX to accelerate KNN plugin, which is one of the plugin that is available in the OpenSearch, right? And few of you may know that SIMD fundamentals, but we'll ensure that everybody at least understand those basic concepts and then move into the AVX. Okay, so with vector search, as I said earlier, that it's not a new concept. It was there earlier. It's actually one of that key feature of an information retrieval system, right? Rather than having the exact search or keyword search, we now have a something called semantic search, which is this meaning aligned? Rather than having a answer that is that the exact search, we transformed into is this meaning aligned with our search, right? So we have come a long way, definitely, almost 8 to 9 years of journey of vector search, vector database. It is heavily being used in AI, RAG, and LLM based search. One key thing I would like to point it out here, You must have heard of different database, structured database, unstructured database, right? And they have their own challenges, especially with the unstructured database, how to store those unstructured data, right? I see vector database as one of the key solutions to address this problem. Rather than storing and thinking about how to store them, we can embed this unstructured data into series of float vectors, typically float vectors, and store them with this. And that will go as an input to any AI system. So I would say it is a pretty standard way of transforming the unstructured data into some sort of giving the concept of structure through the vector database and vector store. Few key concepts I would like to point out here is probably you heard of dense vector, sparse vector, right? Dense vector is nothing but when you have a non-zero element in the vectors. These are called dense vectors. When you have mostly zero element in the vector, it is called sparse vector. Moving forward. Now, we are going to talk about the scale and performance challenge. Vector database as a solution is there, certainly, but that is not, I would not say that doesn't come with the performance and scale challenges. It does come, right? Maybe a few years back, when it was not so popularized, we are dealing with millions of vectors. Now, we have already touched billions and going beyond billions of vectors, right? So it's not easy for any vector store to store those vector size or data size of more than 1 billion or close to 100 billion, right? The challenge is that how we can scale to address the massive growth in the data set. Okay, that's the first thing. And that comes with the challenge with the performance. We need 100 millisecond of, I would say, query latency. That is needed for any chatbot to be more interactive with the user, right? So that's the basic requirement we have. How we can achieve it, right? Because first of all, storing these 100 of billions vector is not easy. Second thing is that how to find the fundamental computation of any vector search. What it is, do you know what is the fundamental computation in vector search? Any idea? Similarity. So how you find the similarity? So yes, please. Yes, distance calculation. So think about this room, right? It's a 3D room, right? We want to keep the vectors anywhere in this room. And when we have the query vector, we want to compute the distance between the query vector and every other vector in this space, right? To find a closest match. That's what the similarity is all about. So the fundamental computation aspect of any vector search is how efficiently you calculate the distance between two vectors, right? And this is the most, I would say, the challenging part of vector search. Okay. And definitely, as I said, it's a compute intensive one. Now, we have enough vector database solutions, right? Vector search solution. OpenSearch is providing that solution through the KNN plugin. But there is always a trade-off triangle, right? Recall is the first one. Any idea about the recall, by the way? Anyone knows what recall is? Exactly. So when you search in that relational database, it's a binary search, right? Binary search in the sense whether you get it or not, right? You'll be prompted with that, I didn't find the data, what you are looking at the worst case. But the beauty of vector search is that it is trying to find the closest search, right? Maybe you are searching with Java. If it is not there in the database, it will try to find a closest match, maybe Kotlin, right? Which is again a JVM based programming language. So it tries to give you that closest match based on your input. Okay, it will not say that the search didn't find the exact match. So recall is an aspect that we always try to find out. Whatever index you follow, whatever index you apply, we measure the quality of the search through the recall value. Recall value gives you that idea that if your search is closest to that input query or not. So the desirable number is definitely 90+%. Then throughput is query per second, right? How many query you are able to execute in a given second, given unit of time, and then resource efficiency. So initially I talked about hundreds of billions of vectors, right? Storing them is not an easy job, right? Each float value, if you take that element or store with a single precision number, right? Each float value consumes how many bytes? Any idea? Any guess? How many bytes each float value consumes in memory? 4 bytes. Okay, so 100 billions into 4. This is a simple math. That much amount of byte you need to store those vectors, right? It's an enormous size that you need. And to calculate those distances, you understand those 100 billion vector, you have one input query vector. Are you going to search with all 100 billion against all 100 billion vectors? It's nearly impossible, not compute friendly stuff, right? That's why the concept of index came into the picture. How we use those index, how we actually generate those index defines the resource efficiency. I'll cover more in the next flip side. Okay. And now quick introduction about the vector search in OpenSearch. As I said that we have this KNN plugin in OpenSearch through which you can certainly get that feature. By the way, I forgot to mention the vector database. If you look at it, right, almost every database vendor is trying to incorporate this vector search, right? So it became a feature rather than a standalone application. I can name a few other than OpenSearch. You have Postgres, we call it as PG Vector. They offer this vector search through the PG Vector, which is again a plugin kind of in the Postgres ecosystem. Okay. So KNN plugin, it supports various backend index engine, okay, to how to store. We have something called FAISS. FAISS is nothing but is a Facebook offering of AI for similarity search. Okay, we have something called Lucene as well. OpenSearch integrates with Lucene. Lucene, if you, I'm not sure whether you are aware of it or not. One of that, I would say, the top information retrieval library written in Java, right? Close to 25 plus years of existence into the open source. What does this KNN plugin offer? It offers the approximate as well as the exact nearest neighbor search. So when you see a movie, right, watch a movie in Netflix, it tries to capture the different aspects of the movie, and it will recommend based on your preference, based on your watch history. It is trying to give you the recommendation, right? What movie you can watch next, probably in the next weekend, right? It can be exact nearest neighbor. It can try to find the exact nearest neighbor. It can also try to find the approximate nearest neighbor. Let me clarify this a bit. What exactly mean by the exact and approximate? Exact means you have raw vectors in this room, right? In the 3D dimensional space, you have 100 billions of vectors. Now you have a query vector, okay? What it does, it tries to find that distance calculation across 100 billion vectors and rank them based on the score, distance score, okay? And then give you the top 10 or top 20 based on your criteria, right? Now you understand, right, how much compute you are spending here, right, for distance calculation. Now, one way to efficiently does this similarity search is something called approximate nearest neighbor. The approximate nearest neighbor suggests that you don't have to do this distance calculation across hundreds of vectors, billions of vectors. Rather, you can create the index in such a way that your search space is smaller, right? And you definitely have a hit with the recall value, but that is something we can tolerate, right? Maybe if it is around 90%, that's more than sufficient for us to say that the similarity search is okay for us. So going next, FAISS, right? Again, a small introduction about FAISS, Facebook AI Similarity Search. It's a library, first of all. It's not a standalone application. Lucene is also a library. FAISS is a native library, I would say. It's not in Java, of course, like Lucene. It does definitely provide the fastest nearest neighbor search on dense vector. Dense vector, I have touched on this. Dense vector is nothing but you have most non-zero element in the vector itself. It supports indexing, clustering, quantization. Anyone knows about the quantization? What does it mean? Any idea? So quantization is a technique through which we can use our resources efficiently. Scalar quantization is one such concept. We have different concepts like product quantization, binary quantization. So there are different concepts to reduce the memory requirement to store the vectors, right? Floats are of 4 bytes, right? It's a single precision float. If you want to store 100 billion vectors, definitely you need at least 100 billion into 4, those many bytes, right? Can you use some technique to minimize our memory requirement? Yes, there is a technique, and that technique is called quantization, okay? You can transform this single precision float number into half vector, half precision ones, right? And it takes just 2 bytes instead of 4. So straight away you are minimizing your memory requirement by 50%. So FAISS support it, right? FAISS has a different quantization technique available. As I said, scalar quantizer. I think we have binary quantizer as well. So other than supporting quantization, as I said earlier, it supports the ANN, approximate nearest neighbor. And definitely it has the potential and it can scale with the billions of vectors with the advanced indexing strategy. Okay, FAISS index structure, it supports flat. Flat means exact search, right? Without any quantization. And then we have IVF, inverted list based one. And then we have HNSW, which is graph based ANN. Now we are going to talk about smarter computation with SIMD, some basic stuff about SIMD, and we are also going to touch base on the AVX part. So I'll hand it over to my colleague Abhijit to take us through this slide. Abhijit.
Hi everyone. So these are the core concepts as Sourav talked about, like similarity search is compute intensive and the heavy part is the distance calculation, right? So the challenge is to enhance that, make it faster. So this is the core concept which helps in enhancing that. So we have a hardware feature which is SIMD, which is single instruction multiple data. Okay, so we can apply a single instruction on multiple data to get the faster results. So as we know that it has FA16, 16 floats, or FP32, which is 4 bytes precision float. So we want to have more of that data into our memory and handle them in parallel. So that is where these vector registers come into play. So we have, if we take 512-bit vector register, so it can accommodate around 16 floats, and if it is FP16 bit this one, it can accommodate 32 floats. So we can do the calculation with 32 floats at a time. So that is the advantage of having this, and this is at the hardware level. So at the program level, we have task parallelism and all. So this feature comes at the hardware level, where we are parallelizing at the data level to achieve more computation efficiency. So the instruction set which offers these features are this advanced vector extensions from x86 platform. So earlier we had SSE, which is streaming SIMD extensions. So that was with 128-bit support, which is YMM registers. So that got doubled in AVX and AVX2, which is with 256-bit vector registers. And further in AVX3, it got again doubled to 512-bit vector registers. So with this, we can accommodate more data and we can do faster computation. And this is crucial for distance metric calculations. For example, Hamming distance in FAISS, it is used in the binary quantization, which we will touch base upon in further slides, and all other distance metric calculations like L2, cosine, etc. Okay, so how that is used in the FAISS with the Hamming distance and all, Sourav will take it over.
Okay, thank you. Just to touch base again on that little bit more information about SIMD and AVX, right? Abhijit explained it quite well, but I just wanted to touch base on another point. You might be here you may heard that something called we have multiple cores in our system, right? We can use multiple threads to execute different type of transactions, right? This is a bit different from that, right? So here we are only talking about if you have a similar instruction like this one on the left side, right? You have two arrays, array A and array B, and you have same operation to execute on those elements, right? The typical approach is that if you have a for loop, right, you can go through it in a more scalar way. Every cycle you try to calculate only one element, right? But with the SIMD concept and with the help of AVX instruction, we can pick up multiple elements and execute the same operation in a single cycle. And that's the beauty of SIMD operations, and that's the beauty of AVX available on x86 through which you can achieve it. If you have any questions around it, we can definitely try to answer those at the end of the our talk. Okay, so here I'm going to talk about how FAISS and AVX-512, right? That's a wider register support on that x86 comes hand in hand to offer you that performance and efficiency both, right? As you know that FAISS binary supports binary indices, right? Like binary flat, binary IVF, okay? Anyone knows what binary vector is? Any idea? We talked about dense vector, sparse vector, and there is another term called binary vector. What it is? Any idea? It is in 1 on 0, absolutely, right? So you probably understand that converting a full precision float value into something into zeros and 1, it will definitely save a lot of space, but that comes with a penalty. What sort of penalty it may incur? Any idea? Recall may drop, right? So to address this drop, right, we have different ideas that how we can bridge those gap with recall. Okay, so here we are going to talk about the binary vector. Now you know what binary vector is, and there is a typical computations involved here called Hamming distance calculation, through which you can definitely calculate the distance between two binary vector, right? Again, 100 billions of binary vector, you have one input vector. How we can calculate this distance efficiently to reduce the computation power and to use the memory efficiently. Okay, Hamming distance, how it is being calculated? It's a scalar pop count, right? I will quickly go through this slide first before coming back to the earlier one. Why Hamming distance and what is Hamming distance and how this calculations happened, right? If you look at this, these are, I hope you're able to see my pointer, right? These are your vectors, right? Binary vectors, ones and zeros. You do a XOR operation on A and B. XOR operation gives you output if you have a dissimilarity between the vector, between the bits, right? So 1 1 gives you output 0, 0 1 gives you output 1. Similarly here output is 1 and the rest of the stuff is 0. So it gives you the number of ones through which you can identify where exactly the bit differs into the input vectors, right? So Hamming distance is basically, here is two different bits, and the pop count, this function actually counts the number of ones. Okay, so it has to go through this A or B output to calculate the number of ones. Okay, it's a scalar approach. Now calculating the number of ones through the scalar approach, definitely it takes time, right? How we can address. I'm coming back to the earlier slide to make sure that you understand that how AVX-512 helps or unlocks to have some sort of parallelization to parallel pop count. Okay, we have something called this intrinsic, which actually emits vector instructions through which you can calculate this Hamming distance in a vectorized way, and you can have a better efficiency in terms of computation, and that computation is definitely way faster than the scalar one. Okay, there is a concept called CPU cycle, right? CPU cycle is nothing but the how many cycles you spend to execute one transactions, right? Let's say it spend 10 cycles. I'm just getting into some sort of very basic example. Let's say one instruction takes 10 cycles to execute, okay, through scalar pop count. You will definitely get less than 10 when you use the vectorized version of pop count, right? That's the beauty. I'll have few slides which can show you that what are the gains, tangible gains you can see in OpenSearch for Hamming distance through FAISS, definitely. Because Hamming distance is a part of FAISS, OpenSearch consumes through KNN plugin. By the way, about the availability of this, anyone using OpenSearch 2.19, definitely you will get this feature already enabled by default. And to maximize performance on latest Intel Xeon processor, you can have these instances, 7i instance, C7i, M7i and R7i instances. You can use those instance type on AWS to get the advantage of this 512 bit of wide parallel pop count. Okay, so I covered this Hamming distance slide. You understand probably that lower the value, right, it is more similar, right? If the value is lower, it is calculating the number of ones. If the value is lower, definitely it's more similar. Had it been the value of differing bits is 5, definitely A and B are not that similar, right? Here it is 2, so you can say that A or B are pretty close. Now I talked about how this Hamming distance, right, with the help of AVX-512 can drive cost efficiency. So here are a few data points we have, which we have worked with AWS team. Our team at Intel works with AWS team to make sure that these are validated, and these are the numbers we have, right? So in vector search, right, any search, right, how we actually monitor the performance, right? One is indexing, right? Indexing is nothing but when you index any input data document, right? How many documents you can index, that's actually the throughput. Okay, when you search, how many queries you can execute per unit time, per second maybe. Okay, and definitely the latency associated with it. Latency means how much time it takes to complete that particular transaction. Okay, so here if you look at these numbers, right, in every aspect we'll see a 10% throughput improvement on indexing and search, and a 10% reduction in latency, which is a huge, right? 10% is a huge out of these results. And then I would like to mention that what dataset we use, it's a random binary dataset with 768 dimensions. Dimensions in vector database is basically the number of elements in a vector, right? So 768 is a pretty standard dimensions we have. So it is tested against those, and it gives us a very, I would say, quite significant improvement over that scalar pop count. Yes, yes. So I talked about these instances. These are Intel latest Xeon processor, 4th gen Xeon processor, which are you can use those instances to avail those AVX-512 optimization. Okay, another good optimization that we did along with our AWS friend, FAISS supported AVX2, right? So it's basically AVX2 and AVX-512. The difference between these two is that the width of the register, right? AVX2 256 width supports 256 bit width, and then AVX-512, as the name suggests, supports 512 bit width. Okay, so FAISS supported earlier AVX2. Now our team actually worked along with the FAISS, the Facebook engineers, to get it integrated into FAISS. What we did is that the support for 512 bit width, right? And where exactly we see a huge performance improvement is in the inner product and L2 space type, right? Inner product and L2 space types are nothing but the distance calculation way of distance. We can calculate the distance between two vectors. So it works across, by the way. It is transparent to the developers. Developer doesn't have to worry about it. It works across AP32 encoded vectors and quantized representation of floating point, which is SQ AP16. SQ stands for scalar quantizer. AP16 is nothing but half precision or half vector. Okay. I touched on this, that instead of representing a 4-byte float value into something called half vector, which takes just 16 bit, 50% reduction in that allocation, right? Scalar quantization definitely supports and offers better compute to bandwidth efficiency. We have seen benefit in both indexing and query execution path. I'll come to that cycle spent improvement, right? This is for the inner product. I'll share you this blog which we published jointly with AWS, where you will find a lot of other details, but I would like to highlight here that in inner product type, space type, how just by using this AVX-512, how the cycle spent for specific functions, we brought it down, right? So on that 28.86, this is for the AVX inner product function, we brought it down to 7.32. It's a huge improvement in the percentage of cycle spent, right? Similarly, for other functions also, we have a reduction, which is quite significant. Now, how it actually translates into something very tangible to the user, like in terms of throughput, latency, query per second. Here is the number. Indexing operations demonstrate 9% boost, while searching throughput and latency demonstrate a 7 and 6% improvement respectively compared to AVX2. And I just want to mention that this is against AP32 encoding, where we didn't use the scalar quantizer. We have similar results for scalar quantizer as well, where we use this SQ AP16 encoding. The data representation is, the vector representation is with half precision vector, okay? We have seen 11% boost in index operations, while search throughput and latency both we demonstrated with a 10% improvement compared to AVX2. Okay, quite significant for us. At least I feel that it is worth trying this optimization. If you have an opportunity in your workspace, certainly something that you can think of, right? And as initially I mentioned that we just don't work on the OpenSearch. All the optimizations are available, right? We upstream it back to that open source community, right? Be it FAISS, be it OpenSearch. So you always contribute back to the community, right? We wanted to make sure that it thrives and creates a better space for all of us, right? Okay, so from a business perspective, right, we all talk about TCO. It's not an engineering term, I know. Total cost of ownership, right? Total cost of ownership is nothing but how much resource you spend, right? Be it a compute resource, be it a monetary one, how much you spend to maintain those instances or your infrastructure. That's called total cost of ownership. So if you have a better throughput, better latency, right? Definitely you will not need, if you have a standard, let's say 100 QPS target, right, to maintain, you definitely not need those many instances which you have been using, right? You can manage this 100 TPS target with a lesser number of instances. That's a straight away you can reduce that instance cost, right? The extra over provisioning instances, you can definitely address it through this optimization. It enables smaller, denser cluster, right? As I said that if you have a target of 100 TPS, 100 QPS, you can achieve it through the lesser number of instances. That means your cluster size can be reduced. And certainly it has a direct impact on your TCO as well, okay? We at Intel, especially our team, we have been working with OpenSearch community for quite a long time. And this is not our first optimization contribution, right? We have contributed, if you have come across G standard compression in OpenSearch. Have you come across G standard compression in OpenSearch? Anyone? That we contributed, okay? And then we have provided some tuning guides, and there is another concept called hardware accelerator for compression, QAT compression. We had contributed to the OpenSearch as well. Now, Recently, we have been involved with this optimization related to vector search. It gains a lot of popularity, I know, very recently in 2022. And we have been working tirelessly to make sure that every piece of hardware feature, right, available to the software, and software can get benefit of it, right, and drive efficiency in its core. And recently, the last one which I described in this talk about our binary vector improvements using AVX-512_SPR. Is that it? No, definitely not. We have some other works, upcoming works. We are continuously engaging with FAISS community as well as the OpenSearch community. We are working on supporting the AVX-512 FP16 in arithmetic for the scalar quantizer. The links are there in this slide. You can take a look at it. We are also working on supporting the BF float 16 with FAISS scalar quantizer. BF is another, I would say, representation of floating values. Okay, it came from Google, if I'm not wrong. Okay, Google actually offered this. Then we have another interesting project. Again, I'm not sure how many of you are aware of JVector. JVector again is a library similar to FAISS but written in Java, pure Java. And there is a concept called Java Vector API, which is available in the Java ecosystem from Java 16 onwards, which supports rewriting your scalar code in a vectorized way so that it can take the advantage of vectorized instructions and the vectorized hardware. So we are working on the optimization of JVector. In fact, my colleague Abhijit is working with the JVector community to optimize the JVector library. Okay, and there is a news that OpenSearch is interested. Definitely, they have a GitHub item. They want to integrate the JVector as well as one of their vector search library. Okay, so we'll be continuously working with the different community, be it FAISS, be it JVector, be it OpenSearch, to make sure that all the optimization we have, we can enable them for our user, for our customer. I would like to thank my colleague. We have a team across India and US. Folks are, I have tried to list a few of them, but there are many who actually helped directly, indirectly to help us to not only optimize, but to upstream it to the open source community. And here we are, right? We are reachable on these channels. Please feel free to reach us if you have any questions, be it a technical. It doesn't have to be very business oriented stuff, right? If you have a technical questions, you can well reach out to us. We'll try to help you understand those concepts in a lucid way. With this, I would probably stop and try to answer any questions you may have. Yes, please. Yes. No, that's a good question actually. OpenSearch uses Lucene as one of its backend engine. So if you talk about G standard compression, right? G standard compression, what we used, we have the G standard native library, right? And we need the JNI, right? So we have a plugin concept, again, similar to KNN plugin in OpenSearch, through which we actually integrate the G standard compression. Okay. Similarly, we have the QAT compression. QAT is basically quick assist technology. It's an inbuilt hardware accelerator for compression decompression function. It can accelerate compression decompression functions in a multifold way, right? Again, through this plugin. Yes. Yeah. No. Hamming distance is very particular to the binary vectors, which is where we contributed. The next slide that we provided, right, about the L2 and cosine, that is where we also contributed. But the Hamming distance is very particular to the binary vector. Yes, please. Okay, the very good questions. Let me clarify this, right? AVX is not a new concept, definitely. Okay. Now, what actually differs is the support for different bit width, right? Abhijit talked about SSE, which supported 128 bit. Then we have AVX and AVX2, which supported 256 bit, and then we have AVX-512. If you are using any latest platform of Intel, like C7i and few others, right, you will get it automatically, right? These are enabled there. And if you use our optimization, I told you that it is also enabled by default. So it is transparent to the user and to the developer. You don't have to worry about it. Okay. So I'm there, definitely will be there around. If you have any questions, please feel free to reach out and get it clarified. Thank you, everyone.